the phase shifter here, which only impart a phase to the state 1, to the lower arm, which in this case is corresponded by rotation on the Bloch sphere around the z-axis with angle phi. And then the measurement over here is formally equivalent to a measurement in the computational basis there in the qubit model. So in the quantum eraser experiment, we record the copy this wish path information in a separate beam, and then we make a choice of basis measurement later. So here this corresponding to making a C0, right? And then the state at this point would be this kind of state up to a global phase, right? But the point of the relative phase is phi. Then last time I said that if I do this, or more precisely, if I have to move this away first. So let's say I make the measurement on this ancilla qubit before the final measurement on the first qubit. So I get, after a measurement, I get a classical bit out, right? And then I do a control here. So if the classical bit is 0, I do nothing. If the classical bit is 1, I perform Z. And the claim is that this will restore the quote-unquote interference pattern. Okay, so how does this work? Why does this set up this measurement in the X basis restore interference? Any comment, any question with the setup so far? Okay. So what I want to do here is to apply the principle of defer measurement to push this classical control to the end of the line and see what happens to the circuit. So, okay, I redraw this again. Then there's this C0. Then I do the Hadamard, but now here is the measurement in the Z basis, and I do a control to perform a Z operation on the first qubits. So coherently, this would be the control Z, right? And then I just extend the line there, which we can assume that we measure at the end of both lines. Well, right. So recall that this is the X gauge, right? Control naught is a control X. So I can push the Hadamard back in the circuit. And then X will turn into Z. Okay. Well, since I'm I'm lazy, I don't want to draw again, so I do the blackboard magic. Here. Here. And so now you can see that these two C phase, control phase, yeah, that's it's called control Z operations cancel. Right? So it's cancel. So I can erase it. I move the Hardeman over here. So this measurement, this act of erasing by doing a measurement on the x basis, the crucial point is that the x basis, you can choose the y basis as well, right? But the point is that the measurement outcome, the measurement statistic of the x and y basis has no correlation with information in the z basis at all. It doesn't depend on the relative phase in the z basis at all. You always get 50-50 statistic. And here, by using the principle of deferred measurement, we see that it's sort of a diagrammatic proof, right? That the situation on what we perform on the first qubit line is exactly the original Ramsey interferometer. And so that's why it's sort of a formal proof that you would get the same measurement statistic at the end. And then you see the result. Yeah, see the interference match pattern. In other words, the probability is a function of phi. So maybe I can say that basically this part act as a disentangler. So basically we, this C0 gate here entangle the two qubits and spread the information from the first qubit to the second qubit. And doing this precisely inverts the entangle that we did. Well, so now, okay, what happens if, let's see, does this answer here? Well, I guess in this diagram, the order maybe also doesn't matter, right? The order of measurement, I can assume that, well, I already assume that I measure at the end of both line, but of course I can like just continue this line and then just measure this the second qubit, which doesn't really do anything after this. But then what actually is happening? Well, maybe doing it here in this diagram is kind of bad because yeah, if I want to change the order of the measurement, okay, it doesn't matter, right? Because the principle of deferred measurement means that I can translate this to a control Z, and this is the circuit that we got. So what the heck happened with, well, the scenario where we measure the second qubit after the first qubit? Well, so maybe I want to be lazy again, so I don't want to redraw this. Okay. So after the measurement here, right, so let's work with this circuit. So last time I pull the wool over your eyes a little bit. It's kind of doing things in a way that not symmetric between my discussion between like Z measurement and X measurement. So if I make C measurement, which is not this circuit, right? If I want to make Z measurement on the second qubit, I remove the Hadamard here. So what happened is that, well, last time we sort of discussed about jargon like pre-measurement and stuff too, right? That if I treat a measurement device as a quantum system by itself, then to prepare for the measurement, prepare for the readout of the information from the auxiliary system, I need to entangle it in the right, like in the basis that I want to measure first. And so we already done that. Now, if measurement happens, or if decoherence happens, okay, so let me write this down here. So if decoherence happens, and what I mean is that I just turn the amplitude here into probabilities, right? So this is kind of like a measurement without looking at the results. Right. So this is the density matrix, and then selection of the result happens when I look, right? And I assume that, well, I sort of assume that this is already a classical probability distribution. Not really, right? Because well, but if I assume that here, it means that I have probably 1/2 of seeing this, or probably 1/2 of seeing this. Well, then I branch up here that with probably 1/2 and 1/2 I see the state here and here, right? And in particular, the state of the system, right? If I think of this as system and meter, which would then go on to, go through the Hadamard gate and experience a measurement, then you see no interference, no information about the phase phi. For the X measurement, last time I skipped this state. So what happens here is that we have, okay. I think that the state is like this. Yeah, I hope that the psi is correct. Now, what happens if I turn this into, if I decohere this, if I turn this into set of state with classical probabilities, so turning into classical ensemble, right? Well, so I would, well, I would just find the first, again, I find the first term with probably 1/2 and the second with probably 1/2 also, right? So let's, yeah, just for simplicity, let's call this a state phi. Well, or rather, I kind of want to normalize it correctly. So then I have square root 2 here, right? And let's call this the state psi. And this is the psi perp. Because, yes, I believe they are orthogonal. Right, because minus is equal to having extra phase of pi, and so you sort of move move halfway across the Bloch sphere on the plane. So these are orthogonal state indeed. And so this is a state. This is a density matrix that I would obtain before looking at the result. I don't know how you want to order this, like psi 0 or 0 psi. Well, it's not symmetric, but whatever. Right. And then if I trace this out, if I trace the meter, the second qubit out, of course, so I just sandwich it between the orthonormal basis 0, 1, right, of the second system. So I will have this mixture. And since these two are also orthogonal, this is indistinguishable from the maximally mixed state. And so actually, indeed, what you will see if you make the measurement here without knowing any information about the measurement outcome of the second qubit, you will see no interference. Okay. And only when you look at the outcome of the second qubits, so that you update the your state of knowledge, update the state of the first qubit to be either this or this, that you see a measurement, you see the interference pattern. And so well, maybe you can figure out what this looks like, but for example, in the continuous variable of the version of this quantum eraser measurements, what you see is indeed on the screen is just like a lump here, which basically consists of like two peaks from, the probability of going through the slit 1 or probability of going through the slit 2, right? Like maybe this peak, and then when I sum them up, it's just a big lump here. So if you make this measurement first, whatever you record is just this lump, right? And implicitly, this lump kind of contain an interference pattern here. It's just that you don't see it. But now, if you look at, let's see, if you make the measurement of the second qubit afterward, and then you just pick out, well, let's see how to do this. Well, in reality, what you see over time is not quite this pattern, right? In the sense that this would be what you see on the screen if you perform this measurement, like send electrons through the double slit and then onto the screen, and then for each electron you just see a dot, right, where it lands. But then if you do this measurement multiple times with a lot of electrons, then you will see these dots build up into this pattern. But now if you go back, if you measure this afterward, and then you go back and then you correlate which dot corresponding to either the result of 0 or 1, you can, it's kind of like post-processing by just selecting a sub-ensemble of points in here, and then you will see the interference pattern. But precisely you see interference pattern because you perform what is called post-selection, which is just choosing what to see and choosing what to ignore. Right. Yeah, so if you, is that okay with everyone? So looking at the measurement here of the second qubit afterward, does not change the past, does not change the whatever you record in the from the measurement of the first qubit. It's just that the information, the classical information that you get from the second measurement allows you to pick out the interference pattern, and thus restore in the superposition between the state. Okay. So everybody is happy. Okay. Maybe I should make a comment a bit here. So when I say that state like this is not not exactly a classical ensemble, and by classical ensemble I mean that for example that we actually do have the state 0 or 1. We just have ignorance, right? We have ignorance about whether the state is pure state 0 or pure state 1. But just to emphasize again, so I think I mentioned something like this like weeks before, right? For one, because the ensemble here, the ensemble decomposition here is not unique, right? And also that whenever you have an ensemble decomposition, so let's say this is the mask 1. Whenever I have an ensemble decomposition, so let's see, sorry, P J I J psi J. Actually, I can always think of it as resulting from entanglement with another system, and then take the partial trace of the system away. More precisely, I can how to say this. So to formulate this process is called well, this mathematical process is called purification. So we ask what joint state psi, since I already used psi here, maybe psi, okay, in the joint Hilbert space. So maybe suppose that this is in the Hilbert space of A, right? What joint state in the larger Hilbert space that we can designate so that we can assign so that the reduced density matrix, let's say partial trace of this state with respect to system B would return back the state rho A. Okay. And one way to do this, or recall that the number of pure states in the ensemble is not limited by anything, right? It can be greater than the dimension of the Hilbert space. And what you do here is basically just by inspection. So so I introduce Hilbert space B of dimension m so equal to the number of states, pure state in the ensemble, and then pick with an orthonormal basis. Well, I can use E, I guess, EK, right? Then by inspection, this is the, well, this is called the purification of row A. Well, by inspection, this state will do. So J, M, and then the square root of the probability, and then the state in the ensemble, and okay, I use J, but whatever, right? By construction, right? Because if I trace out, I would perform the partial trace just in this orthonormal basis, and then I would get I would kill all the cross term, and then just get this term in here, right? And so there's another reason that when you see a mixed state, it does not necessarily mean that everything is classical already. Right? Yeah, maybe it's worth emphasizing that this is just this process of purification is first and foremost mathematical, right? Because there may be, you know, states, there may be system that correlated with our system out there, but even if like physically there's no such thing, you can still do this as a mathematical trick. And this technique, so like quantum information theorists usually do this just because dealing with pure state is easier than dealing with mixed state. And so there's so-called the word, the set of belief called the church. Yes. Church of the larger Hilbert space. That, well, whenever you see a mixed state, you just purify it and then think that there's, you know, a larger Hilbert space. It's just that you don't care about the other part. Yeah. Interestingly enough, I guess this is also how the many world people also view quantum mechanics. It's like, okay, since well, okay, if you have not heard of the many world interpretation, the proponent of the interpretation would maintain that their interpretation is just taking the axiom of quantum mechanics seriously without the measurement part. That is, that they take seriously that there is a state vector that evolve in time with the unitary operations, and everything that we see about like measurement and probability is sort of an illusion, in the sense that if I have a superposition of 0 and 1, for example, and then maybe you can sort of, in the minimal interpretation, you can say that it's in the state 0 and 1 at the same time, but maybe like in a parallel universe. And by the change of measurement logic that I discussed last time, well, in the standard quantum mechanics, it will say that if I make a computational basis measurement on that superposition state, there'll be probably 1/2 of me seeing the state 0, right? And then probably 1/2 of me seeing state 1. But in the minimal interpretation, it would just say that there's parallel universe, and in one universe I see this, in one universe, another universe I see this, and this all happens sort of at the same time, if the notion of time makes sense anymore. But yeah, I think the proponent of many-world interpretation would also subscribe to this, because they would say, okay, so like what is the wave function of the universe? Well, then it's like everything is a quantum, is a state vector, right? So the universe itself has a state vector, and then it evolves with unitarily. So that's probably like the largest Hilbert space that you can have, the Hilbert space of everything in the universe. Although the more traditional interpretation, people would adhere to more traditional statistical interpretation, or in other words, like the Copenhagen-ish people would say that the wave function of the universe is nonsense, because the wave functions or equivalent to the quantum state is only there for us to compute the statistics of measurement, right? But then if you have a quantum state of the universe, by definition, there's no one outside the universe that is observing the universe and make measurement and compute probabilities and so on. Yeah. Yeah. So right. Mm-hmm. Mm-hmm. Yeah. Yeah, that's a good point, and it's related to. But what is your question? Is there, or is it a comment that? Yeah, here you can choose any O and B, right? Because rotation here doesn't matter to the, well, doesn't really affect anything physical in the first space. Although, okay, yeah, physical. Maybe, yeah. I guess that would depend on what you compute, right? Maybe some, I don't know, cross operators or, right? Yeah, I guess that would that would depend on the specificity of the problems, uh, because in the abstract it doesn't. Every O and B are like the same. Yeah. Yeah. But yeah, thanks for the question, because it's sort of easily lead to the second point here, is that yeah, you have freedom to choose O and B here. And well, what is that freedom? Well, the freedom is given precisely by the freedom of doing ensemble decomposition here, which we already learned, that's governed by the Schrodinger JW theorem. So back to this uh, connection to the Schrodinger. Okay, so do you remember what this theorem is? So let's recall, if I have two ensemble decomposition of the same row, right? Uh, Meaning that either I have, let's see, maybe I want to make notation consistent with how I did weeks ago. Where these guys are the subnormalized vectors. So if I have the probability here, right? which I call P alpha, and then the normalized vector here, I just lump them together here. And the reason that I do that because the theorem says that if there are two ensemble decomposition, these subnormalized vectors are necessarily related by possibly non-square but unitary matrix. Yeah, it's kind of, the blackboard is kind of busy. So these two are the statements that these two are the ensemble decompositions of the same row if and only if there exists unitary matrix. Now maybe last time I already said that this is a partial isometry just because they don't have to be square. So they can map, right? Because the number of pure state in the two ensembles may not be the same. So those are all the unitary, the degrees of freedom of ensemble decomposition, which would give the same physical density matrix. But now, in the context of purification, or when we have bipartite entanglement, right? So suppose that maybe I would go in the wrong direction here, but suppose that there are two O and B's of the Hilbert space B. Well, I guess this is not the most general because by allowing non-square unitary here, I can also map between O and B of Hilbert spaces with different size, right? But you can try to think about that general case. So say, let's say if there are O and B's, it means that they are related by some unitary, right? So this is the matrix multiplication rules for basis elements. So it's kind of like an inverted. If I want to write the rule for transforming vectors instead, I have I would write the unitary here, and then the adjacent indices would be the same. I just move it there. But here for the basis, this is how it works. The summation is over beta. Matrix element here is beta alpha instead of alpha beta. And then let's say that I have purification. Let's add the as a hat here to distinguish it from phi over there. Let's see if I have this purification here. And then I try to change the basis. So I can think of this as like a physical action on Bob's side, right? On the Hilbert space B. Then I rewrite this here. Then so if now I move this, oh yeah, exactly right. So this is how you transform not the basis element, but how you transform the vectors. Yeah, kind of like this. Okay. And now I need to sum over alpha and then pull the sum over beta out. Right. U is non-square too. Just that is unitary, right? Here would be the new one of the valid ensemble decomposition. Beta. And so physically, this means that, well, if we really have this bipartite entanglement across the two Hilbert space, over here, to realize this ensemble decomposition of row A, and by realize I mean that to make if I have a lot of copies of this state, by realize I mean that somehow we can make it so that the Hilbert space A, so Alice in the Hilbert space A, she has a bunch of system, right? Which is like each one is a subsystem of this joint system. That each one is actually in one of the pure state phi alpha with the probability defined by the probability that is attached to this. And how to do that? Well, to realize this ensemble decomposition, Bob would just measure in this basis, right? And then call Alice and then say how many, like, well, the measurement that I just made, I got this result. This measurement, I just got this result, this result, this result. And then after having done that, at the end, Alice would actually have a classical ensemble of pure state that consistent with this ensemble decomposition. But if Bob realized that, well, Bob thinks that, well, he wants to realize a different ensemble decompositions for Alice, then he would just make a measurement in the different basis, right? And then call Alice, and then Alice will have a different ensemble decomposition. So in a way, this is generalization of quantum eraser. Because over there, for in the quantum eraser case, there's just two choices, right? So Bob can measure in X basis, and then if he finds the state, so Bob, Alice, or originally I labeled this as system and meter, right? If Bob finds the result 1, then Alice state is this, is 0. 0 if Bob finds the result 1, then the state is the orthogonal state, right? And so in the quantum eraser scenario, Bob realizes the ensemble decomposition of the maximally mixed state of Alice in this ensemble, with yeah, probably 1/2 and half. Right? But here, this perspective of the Schrodinger SJW theorem says that by performing unitary operation that change the basis only on Bob's sides, Bob can call Alice and manipulate her into thinking that she has whatever classical ensemble that is consistent with the density matrix rho. Any any questions? Any things in mind? Mm. Oh, so right. So there are two ways that so this U can map. So let's see. So suppose the index alpha run from 1 to, let's say, n, and beta run to m. So now it depends on, so if n and m's are equal, this would just be a unitary matrix, right? It's just a square unitary matrix. And of course, unitary matrix has inverse. But say, suppose that m is less than n, so you are mapping from smaller Hilbert space to a bigger Hilbert space. You cannot necessarily invert it. Well, sort of. Let's see. So let's say if m is n, so this is yes, so this is one of the Hilbert space. This is one of the Hilbert space. Right? So if I map it to, well, since U is a linear map, so the image, the dimension of the image must be the same as the dimension of the domain, right? And so when you map the vector from here to here, it will sort of just reside in some particular subspace. And then you can map them back one to one, like uniquely by applying the, well, let's say inverse. And the condition, so the condition of partial isometry here is just the same condition as U being unitary, except that it only works in one way. So so here if I apply U first and then apply U dagger, that this is the identity matrix, and this identity matrix in the Hilbert space is smaller, right? As if I define a unitary, I try to define unitary matrix V from here to here. Well, the problem is that there has to be some kernel, right? So it's not really unitary, right? Because to map from larger Hilbert space to smaller Hilbert space, some vector will necessarily go to zero vector. That's a kernel. And unitary doesn't have a kernel, right? Because it's it cannot have eigenvalue 0. The eigenvalue can only be the phase. But then it's sort of, I guess, the condition, okay. So the condition of the partial isometry there would still work. It's just that this would now, we would be, you would only define V and V inverse in this subspace, and then you pad everything else with 0, like row or columns. But then the columns or row that are non-zero would still have to satisfy the unitarity condition, which is that whatever, like the row or columns have to be orthogonal or something like that. Orthonormal, yeah. Is that okay? Yeah, the only reason here that we need this is just because the number of pure state in ensemble decomposition is not restricted by anything, right? It can be any integer. Yeah, so actually this should work the same way here too, like whether the index, the size of the index alpha or beta are like are not equal, one's greater than another, one's fewer than another. I believe if you're careful enough about the unitarity condition here, it's just works exactly the same way. Yeah. Okay, good. So now we'll sort of take the church of larger Hilbert space point of view further, and then say that, well, not only that well, so like in quantum 101, we only have, for a quantum state is represented by vectors, right? Or in this class, I said was represented by arrays, which are like equivalent classes of vector up to like complex scalar multiplication. But now by the possibility of having a larger Hilbert space, or a joint system that you can tensor with the Hilbert space of your system. Now we have sort of extend the notion of state to something more general than state vector. Now we can have density matrix, and because of this, you can always think of a mixed state as as the marginal state of some pure state in a larger Hilbert space. So then there's no reason that we cannot do this with measurement or time evolution either. So you can have a unitary evolution on the larger Hilbert space. You can have a projective measurement on larger Hilbert space. And then now we can start to think about how to describe those time evolution and measurement with operators that only act on our system of interest. And what that accomplishes would be to extend the definition of measurement and time evolution or transformation of states in yeah, precisely. All right, if I have something like this, right, I mean, maybe some density matrix sigma, and then on this larger Hilbert space, I can evolve things unitarily. But then the result here in general, if U is an entangling unitary, you would not be able to describe the final state of the system alone with a state vector, right? It would just be density matrix. And so what I mentioned is that, and maybe, or if this doesn't answer your question, you continue to ask, is that, well, how to think of this as an operation on the original Hilbert space. Well, here I just mean that I have another system. So the initial state is this, right? It can be mixed or pure. And I evolve with a unitary that acts on both of them. Well, and then I will get some state vector out, but this state vector, so let's say B, will in general can be any arbitrary like state vector on the joint Hilbert space, right? And well, to describe the effect that this has on the system A, I would have to trace out this state. So let's say psi down to the system A, right? But then the question would be, well, how to describe this transformation on the system. So let's say this is rho A prime, so this is like transform, so it's already transformed. Yeah, how to describe this time evolution? Because a unitary evolution cannot map pure state to mixed state. It can only map pure to pure, right? Mm-hmm. Yes. So I guess the question is like this, right? If I have rho, but then before doing this, I extend it to basically a choice state with a big Hilbert space. But then this you would sort of act in the obvious way, right? Because this would be U on the system A and the identity on the system B. Well, so maybe there's sometimes that you want to do that. I'm not sure exactly why. Yeah. But I think this will be kind of touches on some point that I want to make later on, which is that the formalism of quantum operation doesn't allow the initial state to be already entangled between the two systems. But yeah, just keep that in mind if you already know quantum operation. If you don't know, then you don't have to think about it. Is that okay? Yeah, feel free to ask questions. Okay, and you can imagine the same with measurement too, right? That I can have a state and then I bring in some ancilla. Again, it can be anything. It can be rho, but then if I don't want to work with mixed state, extend the Hilbert space of this, extend this Hilbert space until the state rho, the mixed rho here becomes a pure state. Right? And then say I can make measurement, could be entangled measurement. So by that I mean this is a basis, so projective measurement in some ONB of the joint Hilbert space. But the orthonormal basis, as we have seen like with Bell measurement, the orthonormal basis of the larger system doesn't, how to say, the orthonormal basis of the tensor product space, you can choose it to be a product basis in the sense that each basis element is a tensor product of just vector from separate space, right? But you don't have to do that, right? You can choose, for example, the Bell basis. which are entangled state. Each basis element cannot be written as a tensor, like a simple tensor form. This is a entangled state. And so you can describe, for example, like Bell measurement, entangled measurement, only with operator that acting on the original Hilbert space with the new formalism too. In particular, projective measurement will be extend to what is called POVM. And by now, nobody knows what POVM stands for anymore. They just call it like this. It's originally from mathematical literature, I think, and it was positive operator value measure. So it's not even an operator, it's a measure. I don't know how many hyphen I have to have. And if you want to know, you can ask when I define the POVM. If you don't want to know, then it's okay. And the funny thing is that actually what people call this generalized measurement, I think depends on like countries or culture also. Some people just call it generalized measurement or generalized observable or something. I think the Russian literature didn't call it POVM. It's just kind of like American ways or something. And let's see. What's the word I want to use? Okay. Maybe there's not enough space. Let's move to here. Oh, now I know what I want to change this to. Yeah, sorry about it. So I will rewrite that the left-hand side. So let's be precise. So basically, POVM give measurement statistic. Yeah. Or what this diagram, I guess, intends to say is that going forward, measurement statistics will be given by POVM rather than projectors. And then post measurement states will be given by trace decreasing quantum operation. And then, well, post measurement state, so the state after the measurement, but without looking at the result of the measurement. outcome will be given by trace preserving. Quantum operation. So we also see that this is sort of equivalent to just tracing out other Hilbert space completely. Other degree of freedom or system. So here are just names, right? So I haven't told you what POVM are. I haven't told you what quantum operations are. So first I can list the difference between the old axioms of projective measurement and new axiom of POVM. So there'll be no physics here, but of like how to realize this measurement. But you work out in homework 4 problem 3 how to extend rank 1 POVM to projective measurements on a larger Hilbert space. Or speaking like in the opposite direction, right, that you can realize a POVM for that problem, rank 1 POVM, by making projective measurement on a larger system. And then within the description of that measurement in your system of interest will become POVM. Right? So here for projective measurements, the probability of obtaining an outcome lambda, and I use lambda because it will become, we usually think of it as an eigenvalue of an observable too, right? Is trace of projector corresponding to the outcome lambda with the matrix rho. This projector, well, it is a projector because they are orthogonal projector in the sense that these equations hold, right? Just a definition of the projector, but also I guess you need this guy to be Hermitian too. And for the sum of the probabilities to be 1, summing over the projector should give you the identity operator. And the state after measurement here, the density matrix after I obtain an outcome lambda, I just project the original state, right, with the projector lambda, and then divide by the probability over here. For POVM, the probability to obtain an outcome alpha will be obtained from also taking the trace. But this E, so this will be an arbitrary positive operator that is less than one in a sense. So yeah, you remember how this kind of inequality work, right? So over here, it just says that E is a positive operator, but over here it means that identity minus E is a positive operator. And we have seen that in a complex Hilbert space, for an operator to be positive, it is necessarily Hermitian also. And so you can diagonalize it, and then this inequality says that the eigenvalues can only be positive at less than 1. But we also need the same constraint, so maybe I'll put it down here. Mm-hmm. And it's important to remember that, okay, so these are the only constraints of so E alpha here are often called POVM elements, and then the set without the alpha is called a POVM, right? Which represent a measurement. Right? A POVM represents a measurement. It gives measurement statistics according to this rule. However, it doesn't give the post-measurement state. And maybe let me make a note here. Something to look forward to is that a POVM can have let's say the other way around. So different quantum operations, or you can think in this case like dynamics that give you the post-measurement states. There can be different dynamics that give you like different post-measurement state, but still give you the same measurement statistic, which is what given by POVM. So the way to say this is that there are different quantum operations that correspond to the same POVM. So here, there's no physics yet. I just want to note that this is indeed the most general way that we can compute probabilities from a density matrix, because rho is a positive operator, and I think you can prove that in order to make this trace positive, you need whatever E is here, you need it to be positive as well. And then these two conditions just mean this just mean the positivity of probabilities, and this is the normalization of probability. So this is the most general way to use Bond rule to write, to output probabilities or measurement statistics. All right, maybe you can do a few examples. Oh, maybe another thing that I want to write, but there's no more space. So for projective measurements, there always exists state vector of pure state. So let's say there always exists a pure state. For some for which grammar, there always exists a pure state psi for which some outcome lambda is certain to happen. And by that, what I mean is that if I'm in a state psi, then so if I fix a particular lambda here, since it's a projector, I can find a state psi in the subspace that I project onto, right? And then if I make a that measurement on the state psi, then I will get I will always get the same outcome, which is that lambda. So mathematically, this is the support. This psi is any side such that its support is within the support of that projector, right? This one. However, for POEM, this doesn't have to be true in general. So there can be states for which no outcome is certain. Just because this doesn't have to be a projector. So let's look at an example before we dismiss this class. Yeah. So for example, so this is sort of like a classical way to make observable into POEMs, but this is not the only way. This is not the only thing that POEM can represent. So let's say that basically I want to make either X or Z measurement, but I toss a coin, and then if the coin comes up head, then I make a Z measurement, for example, and the other way makes X measurement. So there's probably 1/2 of making X and Z measurement. So this corresponds to a 4 measurement outcome, right? Yeah, the four outcome measurement, like 4 hyphen outcome measurement. You can order them like in any way you want. So here you have probably 1/2 of measuring Z and then get 0 outcome, the up outcome, right? And then the other outcome of the Z measurement, and then now you have 2 orthogonal outcome of the X measurement. And all of these are indeed positive operator because they're just scale projectors, right? And they actually sum to the identity just because separately each one, yeah, I probably need 104, right? Let's see. Oh, this is fine, 1/2, right? Because this sum to identity over 2, right? Over 2, so the whole thing sum to the identity. And so this works as a POEM, and here the instruction to make that measurement is clear. You just add classical uncertainty, like to mix these two together. But from the factor of 1/2 in front, you can see that the maximum possible probability when you measure any state is just one half. And so given any possible quantum state, there is no state such that you would be guaranteed to get just one outcome all of the time. So it's time now, but maybe something cool to look forward to. Just some comment is that, so in a way, if you think about it, right, this is a simultaneous measurement of observable that do not commute. And so we learn like from the uncertainty principle that you cannot make X and P measurement, the position momentum measurement at the same time. But well, actually the statement just say that if you want to make a measurement such that some state is, there is some state for which is certain to be at a particular position, well, you cannot have the same state giving just one value of momentum, for example, right? So that the product of the variance of the two has to have some non-zero spread, but it doesn't strictly forbid simultaneous measurement. It just says if you add enough noise, and in this case it's factor 1/2 here, you can make both measurements at the same time. So yeah, we will continue tomorrow. ไม่คอมมิว